So Ron, there you go. Ron's joining from Spring Lake, Michigan, class of 78. Woo! It's excellent. So President Kobach was speaking this morning at the breakfast, because if you ever come up here for reunion, there's a whole bunch of activities. Yesterday we went out on the Ranger for a 3-hour kind of a tour, and then there was breakfast this morning, and you can sign up to go to all these different things. But one of the things that he was speaking about was what makes Michigan Tech different from other universities. There's many things, but the thing that really resonated with me was the values. He said it's the values of our alumni and the values of our faculty, that we're kind of a value-driven alumni base. And so I just wanted to share that with you. All right. So I'm going to get rid of this. Got it. All right. So I'm going to go ahead and get started. And I have a few introductory remarks to make. Welcome everyone, those in the room and those who are joining us remotely. And there's now 23 of you. Hello, remote world. Hi, oh my gosh, I've got lots of comments. Hi, Shep. Hi, Fidu. Hi, Ron. Nice to see you all. And if those of you in Zoom, one last time, if you would like to communicate with me, nobody else can see what you say except for me. You just use the Q&A feature part of Zoom. All right, welcome everybody one more time. So this is our second Husky Bites Live. We only do these in the summer during alumni reunion. My name is Janet Callahan, and my role here at Michigan Tech is that I serve the university as the Dean of their College of Engineering, and I'm the host of Husky Bites. And so what is Husky Bites, you might ask? And the answer is it's a free Zoom-based webinar that we also broadcast via Facebook live stream for those who may not have the ability to do Zoom. We record these and post these. We normally hold them on Monday evenings. We start with conversation between 5:45 and 6, and then I introduce the speaker promptly at 6 p.m. Eastern time. Then the speaker speaks for 20 or 30 minutes, and then we have about a half an hour of Q&A, and we always wind up at 7. We used to run over, and we always end up with unanswered questions, and I always have to apologize for that. So we started Husky Bites. We were actually reminiscing about the pandemic, which I know it's not over, but we've certainly kind of moved along. We started it in the summer of 2020, and we started it in response to the fact that we were all kind of isolated Huskies. Our faculty and our staff were isolated. We were all at home. It just felt very lonely, and so we started it to kind of create community. We also started it to kind of debunk the fact, the idea that you cannot teach remotely, because you can actually teach remotely. It's not the same, but you can certainly communicate with people remotely and involve them in the audience, which is why we have Q&A features and things like that. So we started it in summer of 2020, and by the time summer was winding up, many of the Husky Bitesers, as I call them, contacted me and said, please keep doing this, please keep doing this. So we started season 2 in fall of 20. Season 3 was spring of 21. 4, 5, and now we're in season 6. And each time we do it, our audience just keeps growing. And so the reason we're continuing to do it is still for the community, but it's also because we have a whole bunch of curious people out there, and it's not just alumni joining us, although over 50% tend to be alumni. It's also, I've got school teachers joining us. They can get I can sign off on their professional development when they join us, because we're always learning something new. And so while it's still fun, and while we're still communicating about Michigan Tech to the outside world, we're going to probably keep going. So season 6 is going to begin September 26th, and then we will have a 9-show season. The last one will wind up the Monday of Thanksgiving week. So our first talk of the season will feature civil, environmental, and geospatial engineering faculty member Pasi Lautala, who is the director of our rail transportation program. And the title is Railroads Back to the Future. And the last one of the season will be the geology of the Keweenaw, featuring Bill Rose, one of our beloved faculty members. And now, I'm very pleased to introduce today's speaker, John Lenters. You've been able to see his bio the whole time, so I won't read off where he earned his degrees from. What he's doing now is he's a research scientist here at the Great Lakes Research Center, and he joined us in the pandemic, in the heat of it. He also teaches for us in 2 different departments, both civil environmental and geospatial engineering, and in our MEME department. His expertise is in lake evaporation, Great Lakes weather and climate, surface waves, air-sea interactions, autonomous buoys, watershed hydrology, and physical limnology, whatever that is. People in the room, again, you can ask questions via Q&A, and you can ask them as you go along. People in the room, hold your questions to the end. And with that, John, please take it from here.
All right, thanks, Janet. Answer to the first question of the day is it's physics of lakes. I'll just minimize the screen here. All right, so thanks everyone in the room and everyone online for joining us. And I did want to mention that I'm not going to go back that far to when I was a kid, when I was watching the weather along Lake Michigan, but I will give a little bit of history going back to my days at University of Nebraska. There I am retrieving a buoy in partnership with Northern Michigan University and Superior Watershed Partnership in Marquette from a few years ago. So there'll be a little bit of history to this talk. Let's see if I can advance here.
John, there's now 30 remotely.
Great. There we go. Okay, so that was my background, but I wanted to make clear that this is by no means just me involved in this research. It's a large effort from many different collaborators and organizations over the decade, really. I'd particularly like to give a shout out to Peter Blanken and Chris Spence and Will Hedstrom at UC Boulder and Environment Climate Change Canada for their efforts on the Great Lakes Evaporation Network, which I'll be talking about a little bit today. The GLRC research staff, particularly some of the close collaborators over the past decade or so, Dr. Guy Meadows, who is the founding director of the Great Lakes Research Center, and Dr. Pengpei Shi, who is a hydrodynamic modeler and has worked with us in the Glen Network. And then finally, one of my early students, Carly Leonard, who's since graduated, but did some research using the data from these buoys that I'll be talking about. And I wanted to say, I almost changed the title to Buoys, Lighthouses, and Ships, because I'm going to show a little bit about some measurements we're making from a Great Lakes ore carrier. So this is just a brief overview of what I want to talk about. What are we doing on lighthouses? Well, quite a few different things, but I want to speak mostly about Great Lakes evaporation and ice cover. And then the buoys, I'll explain what I mean by measuring the invisible weather and waves, but in particular be showing some record-breaking storms and Michigan Tech's recently expanded spotter buoy network. So first off, a little bit of background. Why are we studying evaporation from lighthouses? Why is evaporation important at all? This is a graph showing what we call the water balance of Lake Superior. So it shows the precipitation, evaporation, runoff from streams, and diversions, which are quite small into and out of the lake, as a function of the month of the year. And then the flux there is shown in centimeters per month of water, but also on the right-hand side, I'm showing the number of Niagara Falls as a visual. So evaporation, and I'll just use my mouse here so folks online can see this. Evaporation peaks in winter, which might seem surprising, but it's when the difference in temperature between water and air is the largest. And it peaks in winter at about a rate of 2 Niagara Falls. So it's an invisible, largely, flux of water into the atmosphere at the rate of 2 Niagara Falls on average. On peak days, it could be more than that. But this is on average. So it's a very large component of the water balance. You can see it varies a lot from 0 to 2, much more so than precipitation runoff do. So that's one reason why I study evaporation. It's large. It affects a lot of different things. And I'm just showing here water levels. This is Lake Michigan back in 2012 when it reached a record low in response to an early start to the evaporation season on Lake Superior. But it affects also the temperature of the lake because evaporation is a cooling process. Because it affects temperature, it affects circulation, it affects the lake ecosystem, the lake chemistry. So it's a really important physical process. We also know it's variable in space and time. And on the left here, I'm showing the Great Lakes surface water temperatures as measured by satellite just yesterday. And you can see there's a very large difference in water temperature between 80 degrees or so down in the southern lakes to about 40 degrees in the middle of Lake Superior. And water temperature is a big driver of evaporation. So that evaporation rate will vary just like the temperature does. And we've also seen evidence from models that evaporation has been increasing over the decades because of the warming of the lakes and other factors. Another reason to study evaporation, it actually was not measured before 2008. So this is a graph showing the number of rain gauges in the Great Lakes Basin back in 2000, the number of stream gauges and the number of evaporation gauges, which was in fact 0. That's why you don't see any dots on the map. But people would argue that even stream gauges and certainly rain gauges on the lake itself are also poorly measured. So all these gaps in the data. And so what I'm mostly trying to get across in the next 20 minutes or so is we're trying to fill these gaps using buoys, using lighthouses, using ships. So building this evaporation network, I was at the University of Nebraska from 2006 to 2013. And in 2009, I installed a station on Granite Island in cooperation with Northern Michigan University to measure evaporation from Lake Superior. It turned out that a group at CU Boulder and Environment Canada had done something similar in 2008. We met each other at a conference and said, hey, let's partner up and start measuring evaporation across the Great Lakes. So Standard Rock and Granite Island, these two lighthouses, were used to do the initial installation of what we're referring to as the Glen network. This is what some of the instrumentation looks like. This is a weather station atop the old bell tower at Granite Island, which is about 6.5 miles offshore from Little Presque Isle near Marquette. And I kind of refer to it as a weather station on steroids. So it's a lot of wind measurements, radiation measurements, air temperature and relative humidity, very high frequency water vapor and wind velocity measurements, a rain gauge, and other sensors that I don't have time to go into. But basically, these two instruments right here are the most important for measuring what we refer to as the fluxes of water vapor, fluxes of heat, fluxes of carbon dioxide into and out of the lake. We have good internet access at this site, thanks in part to NMU's WiMAX network, and you can visualize the data in real time. This is a graph from a while back, but this is a variation in sensible and latent heat flux, so the evaporative cooling and sensible cooling of the lake. We also have some webcams out there coming and going over the past decade, but these are some visuals that we got during one winter showing steam fog coming off the lake, formation of ice, lake effect snow events. We installed a similar camera on Standard Rock Lighthouse in partnership with the Superior Watershed Partnership. This occurred in 2018, and so we got some interesting ice imagery that winter. This is 2 hours later, so you can see how quickly that ice pack changes. And ice is a big modulator of evaporation and other processes on the lake, so it's important that we monitor these conditions. Over the years, the network grew, and this was largely through the efforts of Chris and Peter and their collaborators. They put some installations in the Straits of Mackinac at White Shoal Lighthouse. Probably familiar to a lot of you because it's on some of the Michigan license plates, the candy cane looking lighthouse. Spectacle Reef, and then Peter Blanken, this is the ship I was mentioning. So if any of you see the Canada Steamship Line vessel Whitefish Bay going by, it actually has some of these same eddy covariance instruments on the bow of the ship, and this is him installing it back in 2017, and it's still running. And part of the idea with this is instead of just having a fixed lighthouse that doesn't move, it was just collecting data at one spot. Now we have a ship that plies the Great Lakes at nearly all times of the year, including when there is ice cover at times. So this is the current Great Lakes evaporation network. A number of different sites at lighthouses, including some on Lake Erie and Lake Ontario. The partnership has grown now to include the NOAA Great Lakes Environmental Research Laboratory. And just quickly, you know, some of the things that we've been learning, you might think that ice cover and evaporation is a relatively simple relationship. In a cold winter, you get a lot of ice cover and it just caps evaporation. It shuts off that flux of water into the atmosphere. And then maybe in a warm winter, with all that ice gone, the lake is just free to evaporate. And it turns out that's not the case. It's quite a bit more complex than that. And it relates to other meteorological factors. It relates to lake surface temperature. And this is just a simple illustration of this. Chris and Noel did an analysis of their data from Standard Rock for 4 different winters, so 2008-9 all the way up to 2011 and 12. One of which, to the start to this, was a high ice winter, and the next 3 in a row were low ice winters. And they accumulated the evaporation. So this is the cumulative evaporation from the start of each evaporation season in about June 1st to the end of the next year. And 3 of those years landed up pretty much right on top of each other without much difference. There was one year, however, that stood out. And it wasn't the first low ice winter, it wasn't the 3rd low ice winter, it was the 2nd one. And it also turned out that in 2010, the summer of 2010, we had really warm summer water temperatures, and there was about a 1 or 2 month early start to the evaporation season, which you can see here about July 1st. And so it got a head start, and then by the end of that winter it was 25 centimeters, about 10 inches of additional water loss from Lake Superior. So, you know, what's going on there? I did have a student at the University of Nebraska do an analysis, and I don't want to go into too much of the details of the statistics here, other than to illustrate that this is the ice covered period here, and we're doing a correlation between ice cover, or ice duration specifically, and the amount of evaporation coming off the lake. And what we found, you don't see much in the way of these black bars during the ice covered period, meaning that evaporation didn't really care what was going on with ice cover during the ice covered period. What mattered was before and after. And what we found, this indicates that there was large evaporation that led to high ice winters and very low evaporation the following summer. And so because Lake Superior is so deep, there's a lot of leads and lags in the system. Think of evaporation as like the cooling process. When you get water evaporating off your skin, it cools your skin. In order to get a lot of ice in the winter, you need a lot of evaporation to cool off the lake. So that evaporation happens first, cools off the lake. You then get a lot of ice cover, which might shut down evaporation, but you already got a lot of evaporation leading up to that. So there's this really interesting lead and lag. And we had some publications related to this, partly using the data from this network to understand that. So I'm about halfway through, and I'm going to switch over to buoys now. So these are a little bit more mobile than lighthouses. And I want to focus on, we're doing a lot of different things with buoys and other more mobile platforms, but I just want to focus on a few things. And I'm going to transition from the Glen network. So the Great Lakes Evaporation Network, we've been trying to promote this as it's more than just evaporation. And you can look at this, if you look at the Mesonet observations from the National Weather Service in Marquette. Mesonet is just a fancy word for a high density weather network. And you notice that there's no such thing as high density out on the big lakes. If you get a weather station out anywhere, it's a big advantage when suddenly something pops up that they can get data from. And this Granite Island station, which is a part of the Glen network, was not there prior to 2009. Well, shortly after us putting it out there, we got this hurricane wind gust at the island that was not picked up by any other source. In fact, I was driving across in the Sioux on the international bridge, and I got a phone call on my cell phone. It was a weather service calling me, and they basically said, "What's wrong with your weather station? We're getting a hurricane wind gust. Can you check your instruments because we think something's wrong?" And so I did. And in fact, when I buried into the data and saw every 10-second measurement, there was a gust that showed up over a 1 minute interval. I called them back and said, "No, it's real." And they looked, and there was a thunderstorm outflow boundary that had gone past the island. It wasn't picked up by anything, and it just showed up at our island and it was gone. And so it kind of freaked them out because they're like, what else is going on out on the lake that we just aren't measuring? Because there are no eyes on the lake, and so I started referring to this as the invisible weather that goes on out in the lake, and just because we don't know it, we're not measuring it. So we need more measurements. And this also applies to waves. So back prior to 2015, there were no buoys on the largest lake in the world in this section, commonly referred to as the shipwreck coast of Lake Superior. So many shipwrecks have gone down, including the Fitzgerald, one of the more famous ones, 15 miles offshore of Whitefish Point. And so I had transitioned back to the Great Lakes at this time. I was working with Limnotech, and we wrote a proposal with NMU and SWP to get some buoys in this sector. And so we did that, and Granite Island was one of the sites because we have really good weather measurements there. We put one at off of Grand Island in Munising, and one off of Grand Marais, kind of on the way towards Whitefish Point. This is what the buoys look like. We actually have them down in the basement of the GLRC now. If anybody wants to go on a tour afterwards, these are sort of famous buoys because these two in the picture ended up measuring the largest wave heights ever measured on the Great Lakes. Just an idea of what they measure there. They would measure and transmit every 10 minutes. And before I show you the results of that big storm, I just want to make sure we're all in the same playing field here in terms of basic wave statistics. So you're probably familiar with wave height, just the height from crest to trough. Wave length is the distance from crest to crest or trough to trough. And then as the wave goes by, there's the amount of time between one peak and the next one. That's called wave period. And what the buoys report are something referred to as significant wave height. And you can find that on this wave distribution diagram here. So if you go out right now and keep it on a waterway, there's a whole distribution of waves coming by, small waves, big waves, some in between, and they typically look like this kind of distribution. And the peak is what you might refer to as the most common wave to go by. The average is a little bit larger than that, the mean. And then there's this highest 1/3 of all the waves. And if you average those highest 1/3, you come up with a metric known as the significant wave height. And I've been told just anecdotally that this is because when mariners are out on the water and they report the wave heights they see, they tend to exaggerate it. And so they think they're this large. And on average, they're actually quite a bit smaller. But since this is what people are seeing, this is what we're going to report. Now, what I want to caution you with there is that's not the largest wave. That's the average of the highest third. The largest wave can be easily 2 or 3 times that amount. So if you see a buoy that's reporting 5-foot significant wave heights, that means that 3 or 4 times within an hour, you might see a 10 to 15-foot wave come by, a rogue wave, as you might call it. So there's a big difference to understand there. And this is something that we need to communicate better to boaters as well, because they think of this as, oh, it's just there's just 1-footers out there. Well, it means you'll see a 3-footer in a 1 hour time period. So, to help this, one thing we've done over the years is add webcam imagery to the buoys. And I put this picture of me in Alaska back in 2012. Partly because if you look at this buoy, these are buoys that Michigan Tech has as well at the north and south entry of the Keweenaw. There's a webcam on this buoy that we put on to monitor snow and ice conditions on this frozen lake up in Barrow, Alaska, that gets about 6 feet of ice in the middle of winter. And as I was transitioning back to the Great Lakes, others kind of caught on to this idea and like, let's leave these cameras on and start measuring, making videos and imagery of what the waves look like. And so we did that with this Munising buoy. And I'll just scroll that video there so you can see what it looks like. And, when you start posting stuff like this for people to see, in addition to the wave data, they get a much better visual for what the conditions are actually like out there. This camera was actually sponsored by Pictured Rocks Cruises and the Munising Visitors Bureau. And Pictured Rocks Cruises would have this up at their desk, and they, passengers would say, we really want to go out today. And they're like, this is why we're not going. And they point at the video, and people were like, oh yeah, okay, I understand now. So we started doing this with other buoys as well. So this record-breaking storm, October 24, 2017, we had what's called a bombogenesis come over the Great Lakes, just a very rapidly deepening low pressure system. And just 2 years after we deployed those buoys in 2015. And so we just happened to measure the largest waves ever measured on the Great Lakes. 2 buoys, actually, Granite Island and Munising, both hit 28.8 feet within a few hours of each other. So it's not like it was just a fluke and one buoy like, I'm not sure about the data. The other buoys showed the same thing, and one of them actually won by 1 inch, but it's within the noise of the data. And it turns out we actually had a buoy out at Standard Rock that same year, and it only measured 17 footers. So you might think that, the biggest waves are way off in the middle of the lake. Well, not in a northwest gale. They're actually right along that shipwreck coast. Standard Rock did have the highest winds, though. We had some hurricane wind gusts during that storm, blew everything to shore, and we captured this event. Now, are these the highest waves ever on the Great Lakes? No. Clearly, all we answered was we needed these buoys out a lot longer ago to measure what's going on out there. We're probably going to break this, somewhere, sometime. We did actually find out from a simulation that the biggest waves were somewhere between Munising and Granite Island. So we missed the biggest, even though we had 3 buoys that were never used to be any. Fondrest Environmental picked up on this because they are the company that makes the buoys, and they wrote an article on this little buoy, big waves story and showed the time series from Granite Island. And then, I moved to Michigan Tech starting in 2020, and Michigan Tech already had a well-established buoy network, 3 buoys over different time periods, starting in 2010 with the North Entry buoy. Looks very similar to this one. You can tell that this is the one that's in the Straits of Mackinac, because you can see the bridge in the distance there. But 2010, 2011, 2015, these buoys went out in support of a whole variety of different operations. And then in 2020, we kind of had a unique opportunity with COVID. Actually, NOAA was not getting their buoys out right away. There was essentially a safety issue with mariners, and so we put in a proposal to fund some new spotter buoys, which I'll explain what those are in a second. And we put 3 out in 2020, and then 2021 and 22 with some funding from the Great Lakes Observing System. We expanded that significantly. These are smaller, easier to deploy, report some of the same characteristics, mostly about waves and wind, but also water temperature. And so what is a spotter buoy? We actually have one down in the basement if you want to take the tour afterwards, but this is one of the newer generations. It's really about this big around. Measures waves, winds, water temperature. The new ones measure barometric pressure as well. It also reports where it is, so you can deploy them as drifters. So here's the deployment options. It can be free floating as a drifter. You can map currents on the lakes. You can moor them in a conventional way. You can get what's known as a smart mooring that measures water temperature at depth. And so we put the first one in at Big Traverse Bay in April of 2020. To our knowledge, this is the very first one to ever go on the Great Lakes, and it's down on display in the GLRC. This might go in a museum someday too. It was part of an effort to support the dredging operations out there. So some of you may be aware of the legacy stamp sands, that the legacy mining waste along Buffalo Reef out there. That's a real environmental hazard, and there's a lot of cleanup going on. And the dredging company needed very fine precision weather and wave forecasts, and so we purchased a buoy in support of that operation. We put another one out at Pictured Rocks National Lakeshore because those buoys were delayed in 2020. And eventually another one out at Standard Rock, and this is some results from my student Carly, who presented at a couple of different conferences the results of this work. And you can see the significant wave heights from 0 to 8 feet or so at Gay. Also at Pictured Rocks, and then a 22-footer, 21-footer at Standard Rock from a big gale that year. One thing we did notice too is Pictured Rocks just really stands out as getting a lot of web hits. There's a really burgeoning kayaking community there that travels along that stretch of really dangerous shoreline. You can see from the rocks here in the distance, and also cruise ships and other operations. So with that one being the most popular, we then expanded the network again in 2021 to support other ferry operations on the Great Lakes, including this time Lake Michigan. And this was in partnership with the Northwestern Michigan College in Traverse City. They deployed some down near Grand Traverse. We put one at Washington Island, which gets, I think, over 150,000 passengers annually between Northport, Wisconsin there and Washington Island. And then in support of the Isle Royal transportation, we put one at Copper Harbor and 2 out at Isle Royal. So this is just some visuals of what each of the locations look like. Some of you may have been up to Copper Harbor recently, and this is right where the Isle Royal Queen passes by. There's a spotter buoy now out there supporting their operation. We have one out the west end of Isle Royal that was just recently redeployed this year, a couple of weeks ago. And then this is some of the data we're getting from these. So these, we put smart moorings on these. So we got a top and bottom water temperature sensor. And you can see at Isle Royal, for example, a lot of interesting water temperature dynamics going on here, where you have upwelling and downwelling and water going up and down and mixing. And we'd have some strange spikes in wave height here that Carly did a research project on and was able to develop a QA/QC routine to screen out that data that's now available to the rest of the community. This was another example from one of our research projects. We thought, well, these spotter buoys, quote, measure wind, but they really don't measure wind. They derive wind from the wave statistics. So we thought, well, how well does that work? And so we deployed it next to one of our tightest buoys here at the north entry. And she did a comparison with not only these two buoys, but also with the lighthouse data to see how well the wind and wave, the wind data in particular matched up. And they're actually pretty good. They break down a little bit at the higher winds because the waves get so big. So finally, I'll just wrap up here by showing you some of the cooler things we can measure with spotter buoys now. And these are drifter experiments where you either let the buoy drift free or it goes rogue on you and breaks its mooring and does it for you. I call this the self-retrieval option that the spotters have. And so I mentioned already the 21-foot wave event at Standard Rock. Well, the buoy didn't really like that. And so it took off from Standard Rock in a strong south gale, even ahead of that storm. And then did this little curve, northwest gale kicked in, it went down here, it did a little loop-de-loop, and that's actually not uncommon on the Great Lakes, has to do with the rotation of the earth. If you just shove the water in one direction and let it go, it'll do circles. And so that's what happened in this particular event. We eventually got out there and got it. That's what those two dots are coming back. This is what that storm looked like. So get ready for a little gale here. I'm going to show you a video. This is the top of Standard Rock from that same webcam. And these are right around the time of the 20-foot waves. Of course, everything's breaking around the lighthouse. This is a fairly shallow reef. And so it doesn't really give you the view of these 20-foot waves coming by because they're breaking and you're looking from the top of the lighthouse, but you can see it's just a tempest. So the buoy by this time was somewhere off here and just trekking on its way to Whitefish Point before we grabbed it. We also did an intentional drifter experiment in partnership with Bloss last year. We dropped the buoy off at the north entry without any mooring and just said, okay, go do your thing wherever you want to go. And we expected to eventually make it to Copper Harbor along the Keweenaw Current. And it proceeded to do the exact opposite. Did a bunch of loop-de-loops and went left instead of right. Didn't surprise us too much, but you know, it's really interesting how often those show up and going the opposite direction of what we think the prevailing current is. Well, eventually, and this is zoomed out now, it did take off and just went on a beeline. And before it went into the shipping lane, we took off from Eagle Harbor and went and snagged it. So I'm thinking we're going to try doing this on a more frequent basis and really start to map out that Keweenaw Current and find out how much does it change from year to year, and how much does it depend on weather conditions and so forth. This was another one drifting with mobile ice. The one in Isle Royal on the western end, for various reasons, had to be left out last winter and got stuck in the ice as we expected it would, and did a little hop along shore with the ice, which started around February 8 to 16, and then kind of just went bye-bye and stopped reporting. And we weren't sure if it was covered in ice, if it was crushed by ice, if it just ran out of battery power. But a couple of weeks later, it came back. A couple of weeks later, it came back again, and eventually drifting with thawing ice, open water, and final landfall. It went just round and around the western arm of Lake Superior for a while before it finally ended on Devil's Island, which is not the island to land on if you're an electronic device and want to keep working. So Devil's Island has a lot of rocks on shore, so it stopped reporting. But it was an interesting experiment, and if we do intentional drifter experiments in the future, we do have ways to design those so they don't actually go all the way to shore. So just to summarize, that's a quick synopsis of things we're doing with lighthouses and buoys, but evaporation and ice cover, I've explained why it's important. It's been understudied. We're trying to fill data gaps in a variety of different physical processes that you can measure on the Great Lakes. We have an expanded buoy network now, providing early warning data to boaters, Weather Service, Coast Guard, et cetera, and revealing lots of complex patterns in lake circulation, ice movement, and local currents. So I'll just wrap up again by reminding everybody that we've got a lot of people to thank for this type of work that has occurred over at least a decade on the Great Lakes now. So many partners that have supported our efforts, and folks that have involved in field assistance and funding sources. And if you want to help fund what we're doing, we do actually have a way to do that now. We started a Superior Ideas project online. You can just Google MTU Superior Ideas Buoys, and you can help fund the buoy network so we can continue to keep boaters safe and do some interesting experiments. So thank you.
Awesome. So thank you, John. I'm just going to get close so people can hear me. Stay close because you're going to be answering the questions. So people in the room, this is a chance to ask questions, and John's going to kind of repeat the question so people out there in Zoom can hear the question. People in Zoom, you're going to scroll down to the bottom of your screen, use the Q&A feature, type your question in, and I will read them out. And I encourage you to ask questions. This is your talk was really fun and kind of nauseating at points, but but the questions that people ask can you never know what they're going to ask. They're smart people. So, all right. So in the room, questions. John, you can.
Yep.
You plan on increasing the number of buoys out there? Is it a matter of funding?
The question is if we plan on increasing the number of buoys out there. The short answer is yes, and these spotter buoys help us do that because they're about a fifth of the cost of what something used to be. But it does still come down to funding, and just buying a buoy that it's maybe double it to cost of operations and maintenance each year. So it does come down to funding. Fortunately, we've been successful in that regard, and a variety of different sources, but we're optimistic that we can do that.
And if you got more buoys, where would you want to put them?
That's a really good question. I mean, there are still gaps in a lot of different places, and it largely depends on the need and the reason, the rationale. So if I just go back to this earlier, this one here. So these red dots show for Lake Superior, at least these are actually this one here is the first one to go out on the Great Lakes in response to the sinking of the Edmund Fitzgerald in 1975. This one went out in 1979. So 4 years after, in response to a very disastrous event, they start putting these out. So it's partly why we and other organizations have been putting them out as well, is to keep boaters safe. So these have been out here a long time. Michigan Tech has had these out since 2010, 2011. But there's, I see lots of big wave events in Autrain between Marquette and Munising. Chris Point has a lighthouse that we have thought about, like pairing up a weather station and a buoy. Whitefish Point is challenging just because of the ship traffic. You have to get permits for these buoys, and getting permitting near shipping lanes, even though you're trying to support the shipping lane, if it's too close, you don't get permitted. But there are other reasons. There's a buoy network in the Apostle Islands that's trying to support algal bloom research. So a variety of different reasons.
All right, we're going to take one from remote. There's quite a few coming in from remote. This is from Ron. Do you have any estimate of wave height when the Edmund Fitzgerald went down?
Yeah, that has been estimated to be around the same as the largest waves that were measured by buoys. So in the 25 to 30 foot range, the estimated maximum wave heights. In fact, there's a hindcast simulation that was done by the NOAA Great Lakes Lab and the Weather Service, and they basically took the weather from that event and simulated the event with a modern wave model. and found that the waves maxed out and converged on the boat at the worst possible place, the worst possible time. And they were around 30 footers. So, and so keep in mind, those are significant wave heights. That means that there was a 60-foot wave somewhere in that 1 hour period. Well, they were out in the boat for hours and hours and hours. So, and this is really important. It's not the average wave height that hurts boaters. It's usually the biggest one. And it's, you know, there's some research going on, including folks at University of Wisconsin, looking at freak waves and what, you know, what kind of event would maybe produce more freak waves than other freak waves. And it's a problem. Yeah.
So one more from remote. What brought you to Michigan Tech, John?
Well,
Besides the
lots of
pandemic.
things. Yeah. Try not to get emotional about this because I came here in 8th grade on a trip to Our World and loved it. 1983. And it was my mission to get here someday.
Hey, you
And
pulled it off.
Honestly, when I was camping on Our Royal, I read The Wreck of the Edmund Fitzgerald by Gordon. No, well, not Gordon Lightfoot was the one that wrote the song, but Jamie, you know his name, the guy in Marquette. Why is it not coming back? Yeah. So anyway, I went back to Our Royal on a later trip and read that whole book, and it was actually just as I was leaving for college. I've been to Our World now 6 times since that first time. I was taking off for grad school, and I had to talk with my best friend, and I said, I think that book and that island have changed my life. And it was in grad school that I eventually steered towards looking at weather impacts on lakes, and particularly Great Lakes. So
Nice. Other questions in the room? 'Cause
Fred
I've
Stonehouse.
got like 27 online.
in case Fred Stonehouse is listening, he's the one that wrote the book.
So are you using the buoys in real time to get wave prediction? Like I'm a big boater, the website I can go to get real time data to see what the.
Well, there may be, but it's not as easy to find as it used to be. And I think the Great Lakes Observing System is probably going to, they have a new website this year called Seagull, which has a lot of fancy new graphics. But one thing the old graphics used to have was not only the current wave height, but a projection from the Great Lakes Coastal Forecasting System model at NOAA of what it's going to be in a few hours. Now that data is still all available in different graphical forms, but it was always on top of the existing buoy data. And so it was nice to have that nowcast, as we call it, and the forecast. If Gloss is listening, maybe it'd be a feature they already have on their page, or it's one that I really think should be added back in. And they do have a comment section on that new Seagull website, because if that's something that you like to see, please ask them to add that feature.
All right, question from online from Jim, one of our alumni. Back in the 1960s, when I attended Michigan Tech, professors talked about a sea captain on the Great Lakes who had been a sea captain for the German Navy during World War II, who said that the Great Lakes were rougher than the ocean. It can make people sicker than ocean voyages. Can you explain why?
Yeah, so that mostly has to do with the wavelength of the waves combined with the wave height, which is a parameter called wave steepness. So on the oceans, since they're so large, you can have swells on the ocean that are waves coming in from, it could be a hurricane 1,000 miles away, and by the time they reach you, they've dispersed, and you've got these long swells coming in. They may be large, you have 20, 30-foot waves crashing on shore, but they're so spread out that even a small boat can, navigate them if they're not breaking. Problem with the Great Lakes is you can develop just as large waves, 20 to 30 footers, but over a much shorter distance. And so then you get what's really called local seas as opposed to swells. We do get swells on the Great Lakes, and the surfers love it. People in Gay, for example, get an easterly wind and then it switches to a west wind, and those lingering easterlies can give you swells that you go surfing in, but it's not typical. It's not like typical in the ocean. So if we get a big storm in the Great Lakes, you're going to see that really localized 20 to 30-foot seas in a big storm. And they just come one after the other after the other. And then as they get to shore, they also shorten up and get steeper. And so that's what's causing problems for the mariners that aren't used to that kind of condition.
Here's a
Yeah.
question.
It just seems like you don't have that many buoys considering the size of the lakes. Couldn't you have a very localized weather system that could cause very localized wave phenomenon, right?
Mhm.
So these buoys seem to be, miles apart.
Yeah.
Right?
Yep. So the question is about the size of the lakes. They're very large. And even with this many buoys, there's still a lot of gaps, and you could have some localized storms that are causing big events. Yeah. And actually we suspected that when we started putting in these spotter buoys, and we immediately started seeing interesting things. So for example, there's a sea breeze that sets up in Gay. A day like today, even yesterday, we had a southwest wind, and the winds are kind of curling into the Keweenaw. So Copper Harbor was seeing a bit of a sea breeze. Gay was seeing a bit of a sea breeze. And even on relatively calm days, all of a sudden we would see a sea breeze kick in 10 to 15 knots, and you'd see 1 to 2 footers at Gay. And, they're not really in the forecast, or the wave models aren't picking them up. So there's localized things like sea breezes. The Gay buoy has also turned out to be an indicator buoy for upcoming severe weather. I started getting alerts on my phone every time we'd have a severe weather event last summer and also 2020. I would get alerts on my phone about the buoy freaking out before the severe weather alert came out. And it happens so frequently. I was like, it makes sense. We get a low to the southwest of us, and we get an easterly wind, and the buoy starts getting bouncy. But it's really striking how frequent that is. Yeah.
Because these alerts, they're not using the buoy data, right? They have other instruments, or they're getting it from the buoy.
The Weather Service?
Yeah.
Yeah, the Weather Service they are excited every time we put out a new buoy, because they're relying on, they used to rely on NOAA. This was something NOAA did, but there's so many places you can put them on the near shore that they are now relying on communities and small, groups of people to put these buoys out. And we've been doing that. And the Weather Service loves it, because they just eat up that data, and they've improved their wave models. We've done comparisons with the wave models, and there are some problems, and putting more data out there helps us improve those models. Yeah.
So we have a question from Shep, who I think is a sophomore here. He says, "Hi, John, what do you think about the current cold state of the lake? More/less snow? Also,
Yeah.
What should us current Huskies keep an eye out for in terms of opportunities to be involved? Maybe getting on the new catamaran."
Right. Well, so we've had a weird summer. If anybody who's been up here has complained about the wind, myself included, charter fishermen, it's been a windy summer. We have had cold conditions, but warm conditions to the south of us. So basically, if you look at a weather map, the jet stream has been hanging right over the UP essentially for much of the winter. And that's unusual. It's normally well north of us into Canada, keeps all the storms up there. With the jet stream right over us, all the storms get steered right over us, and it's the storms that bring in the wind. And I think this is largely related to La Nina, which is a pattern in the eastern central Pacific, that it's part of our natural climate variability, and that tends to cause shifts in the jet stream. Is probably the reason for our cooler air, the cooler lake, our windier conditions. As for what that means for the fall, all bets are off, because I've found, at least from doing different aspects of this research, is that in the fall and the winter, you're at the mercy of what the weather's going to do. The lake has some control, certainly in terms of water temperature, but it's at the mercy of what the weather does. What matters next summer, though, is what happened to the lake in the wintertime, because there's a really deep mixing process that occurs in the spring. So I like to say that Lake Superior remembers the winter. It doesn't really remember the summer. I may change that answer after 10 more years of research, but that's what I'm going with. And as far as getting involved, come down to the Great Lakes Research Center. Sometime we'll give you a tour. We'll give you
The winter is
opportunities.
more impactful you think?
It has a different way of remembering the weather, and it has to do with deep spring mixing that happens in the lake. And since the lake is so deep, it takes a long time for that process to happen.
Because of the evaporation?
No, it's mixing. It's the temperature, the maximum density of water is 40 degrees, and there's some physics involved in that would take a few minutes to explain, but we probably have other questions.
We do. We have some more questions. I think this may be from one of our faculty members, Anna, possibly. We have seen the large cruise ship diverted from Houghton several times this year. Any comments on the economic impacts of the knowledge limitations that exist regarding Lake Superior?
I'm not an economist, so I can't really say much on the economic impacts, but I tell you, I had to shake my head every time I saw that boat getting shooed off. Because, you know, it's partly because we had a windy, cold lake this year, and so the wind doesn't help. The cold water keeps the fog season going longer, so there's fog issues. I think that most of the reason for them not coming had more to do with transporting people down the Keweenaw waterway safely in different conditions. So, you know, there were times I wondered why they got sent away and thought that would have been just fine. And there's times that there were valid reasons, but you know, I think the solution may be in the works with the waterfront being redone and thinking about ways to make it more accessible for big cruise ships. So I think once that happens, that'll alleviate probably a lot of the issues.
All right, I can't see you very well, so chime in if there's questions from the room, but I'm just going to keep taking from online. This is from Stacy, who is a regular Husky Bitzer, which is what you're called if you attend lots of these things. Great presentation, John. Thanks so much. Her question, if a buoy is attached to an anchor, how much extra line is attached so that the buoy can rise as a wave passes?
Yeah, so the ratio of the line length to the water depth is often referred to as scope. How much scope do you have in your line? And we tend to give it at least 1.5 times the scope. So if you're in, for example, we're putting a buoy out at Standard Rock in a couple of weeks, and it's in about 100 feet of water, and we give it about 150 feet of line. So it's and that's primarily so that, you know, if currents are often a concern with these buoys, not just the waves. And that's, if you get a very strong depth integrated current, it can really tug those buoys and the lines. So the deeper the lines get, the more you have to be concerned about scope, because it can just, if there's a strong current, it can pull that line pretty hard and move the buoy. We actually saw 3 buoys move in a storm in November of last year, and one of them busted loose. It went off into Lake Huron. We get to go chase it down. So your question is great. It's something we are concerned about, but we also, with the spotter buoys, you know, we can get away with a little bit more because we don't need as much anchors to hold them in place. And so we can actually pull up the anchor lines, which makes things more convenient. But yeah, the line scope is important.
Great. I know we're coming up on the hour, but I'm in usual Husky Bites timing, we'll end on the hour. So we're going to take a question from Kent. When you say biggest wave ever measured, when did measurements start? He's thinking 2008.
So the measurements started at this buoy in Central Lake Superior in 1979. And these are mid-lake buoys, so they are not necessarily the best suited for picking up the biggest waves. Maybe in the off season, you'll see bigger waves out there, but in a northwest gale, the biggest waves are along the southeast shore, and that's true of any of the Great Lakes. And my understanding from that big wave event was, I wasn't really that into finding out if it was the biggest wave ever, but somebody at Limnotech looked into it. They think they found a 25-footer at the north entry, Michigan Tech. So I think Michigan Tech had the previous record with the north entry buoy, a 25-footer, which is impressive for that western shore. I mean, that had to have been quite a gale to get the biggest waves there, as opposed to maybe, say, you know, again, it could have been bigger down here. There were no buoys at the time, but So, you know, since 1979, that's the biggest one we know of. But I don't like to make a big deal out of the record, except for the fact that it, you know, it points to the fact we don't have enough of this stuff.
Yeah.
There's not enough statistics.
Well, and then the related one. So the biggest wave recorded on Lake Superior was how many feet?
28.8,
All
if
right,
you want to
and-
be precise.
And that means that there were waves that were 60 feet?
2 or 3 times that over a couple hour period, you know.
So biggest wave is basically a misnomer. It's not the biggest wave.
Right, right. In fact, yeah, and you raises the question, what's the integration period of these buoys? You know, some of the buoys, it could be 10 minutes, some it's half an hour, some of them are a full hour. So they're calculating the wave statistics over that period and giving you an average. This happens to be the average of the largest third. That's the significant wave height, but it's not ever really measuring every individual wave. Some technology can do that, and there are people that are doing that, and they're measuring freak waves and rogue waves. But the biggest wave ever on the Great Lakes, a single individual wave, that could easily be 120 feet for all we know.
Oh my God. Wow. All right, and this last question is related to, from Carly, is related to your expertise. So if they remember correctly, summer of 21 was the warmest Lake Superior has been in the season on record. Have you looked at how this has affected evaporation and ice cover this past winter and year?
Short answer is we haven't. We don't have a lot of funding right now for the Great Lakes Evaporation Network. And so we, as Peter kind of likes to joke, but I don't think it's too funny. He said, we have just enough money to keep the lights on at the lighthouse and collect the data, let alone do something interesting with it. And so some of the stuff I showed you is from years back. If it's 2021 was the warmest year, I'm not sure if she's talking about Lake Superior or a different lake.
Lake Superior.
Okay. I don't know if that was really the warmest. I mean, they tend to happen, again, the question about the seasons, it tends to happen after a warm winter. So like 1998 was 70 degrees all across Lake Superior on the surface. That was the first year I think that happened. And then 2012 was a really warm summer. 2016 was a really warm summer. A lot of those tend to be El Nino winters that lead to warm water temperatures in the summer. And actually that graph I showed from Standard Rock, this was one of those warm, this one here. So this was 2010 was a really warm surface water temperature year. So was 2012. And this is the kind of thing that happens during those years. So, you know, I would hazard to guess that probably happened in the warm year that she's referring to. But the thing is, you know, evaporation needs warm water, it needs windy conditions, it needs dry air. A lot of those are affected by lake circulation and ice cover. And so water temperature is only one of the myriad of factors that affects evaporation.
Excellent. All right, well, I think it's time to wrap it up. So there were 32 people joining us remotely, kind of about a dozen or so in the room. John, it was a pleasure. Thank you so much for your time. And one more round of applause. All right, and so people in the room, yeah, so we're gonna go ahead and we're gonna end the webinar. So thanks everybody for coming. Anybody who would like a t-shirt, help yourselves. There's smalls, medium, large, extra large, and you have vintage with that.